Hi everyone, welcome back. Now in this particular lesson we're going to be looking at derivatives and integrals of vector functions. So in the previous section we were looking at vector functions and space curves, and we were able to see that we were able to model certain curves, or let's say intersections of two surfaces, by the method of parametrization. And we did discuss that parametrizations are not unique. And we're going to keep going with that type of argument using that parametrization, especially when we're talking about these vector functions. Now, on the screen here, what I have is the derivative of a vector valued function. And to start off, the definition reads as the derivative r prime of t of a vector function r of t is defined as dr dt, or in other words, the derivative of the vector function r with respect to t. Also, this could be looked at as using the limit definition, limit as h is approaching 0, for r of t plus h minus r of t all divided by h. And again, that's provided that the limit exists. Now, again, when we're looking at this kind of feels very similar to that Calculus 1 definition, where we were looking at functions and their derivatives. However, in this particular case, we're not just looking to subtract two function values. We're actually looking to subtract two vector values. And if you remember, vector subtraction, we have to do term by term. And in the picture that I have on the left here of your screen, you'll see the axes here, the coordinate system x, y, and z. And you'll see this curve on screen. You'll also see a vector shot from the origin to point P, that's denoted as r of t, and another vector that ends at point C, taken from the origin, this is r of t plus h. So given two vectors, or given two different positions of this curve, can we then define a new vector that will be the difference between the two? So we will define this new vector r of t plus h minus r of t. And again, you can do this using the geometric vector subtraction, and you will see that this is in fact the vector that begins at p and ends at c, which will be the subtraction. Now, once we start dividing by h, we then have to keep that in mind, because now we're taking the vector values that we're subtracting and we're dividing by a scalar. Or we can say that we're multiplying by 1 over h. So again, we're taking this 1 over h, we're multiplying it onto this subtraction vector. So in a sense, we then have to figure out what is happening here as your h value keeps getting smaller and smaller and smaller. Right? And that's where we then start talking about this whole idea of having a derivative of a vector function. We want to make sure that that h value becomes as small as possible, and therefore we're going to send it to 0. Now, the subdefinition here says that if we have vector r prime of t, then this is going to be called the tangent vector to the curve defined by r of t at point P, provided that r prime of t exists and it's not 0. So here's where we actually start getting to the more calculus portion, saying, hey, we actually know these rules from calculus, from Calc 1, when we started finding derivatives of functions and then working with the tangent of a function at a given point. Furthermore, we're going to keep defining these functions. So what we have here at the bottom of your screen, this says that if r of t is equal to a vector valued function, f of t, g of t, and h of t, where f, g, and h are differentiable functions, then r prime of t is made up of the individual components when we take their derivatives. In other words, the first component, f prime, second component, g prime, third component, h prime. And what we want to do now is we want to start employing this particular derivative process. So on screen here, you now have this example. This example says, find r prime of t for the vector-defined function. And we have the vector-defined function here, which is r of t is equal to the components, the x component of 8t to the power of 7th, y component cosine of 2t, and the z component natural log of t plus 2. All we have to do is then take the derivatives here. So I'm going to say here that I am taking the derivative with respect to the variable. So that's the derivative of r of t. And I'm going to apply that derivative onto each individual component. So the derivative with respect to t for 8t to the 7th, the derivative with respect to t for cosine 2t, and the derivative with respect to t for natural log of t plus 2. Now we just go through the derivative rules. So here we now have vector valued function r prime. This derivative here, 8 times 7, will then get us 56. So this is going to be 56t to the power of 6. And then derivative of cosine is going to be negative sine. So we're going to have a negative sine of 2t. However, we need the chain rule, and the chain rule is going to multiply by 2. And then we need this derivative here. So the last component derivative, natural log of t plus 2, that's going to be 1 over t plus 2. And if we take the chain rule of that argument, it's just 1, so that derivative is just multiplied by 1, or that last component. And this is your final answer. Again, all we're doing is taking these derivatives term by term. Great. So if we can look at derivatives for these vector-valued functions, then naturally we will also be able to look at integrals for these vector-valued functions. And I will give you those definitions in just a bit here. All right, so here we are. Now, we're looking at the indefinite integral, and we're also going to be looking at the definite integral for a function, a vector-valued function, r of t. Now, both of the definitions are on screen here. And again, they're going to be very, very similar to what we have from Calc 1. We have a indefinite integral for a vector-valued function, and when we calculate that indefinite integral, we must always account for the constant of integration. However, in this particular case, you're going to notice that the constant of integration is going to be a constant vector. So we have to make sure we keep that in mind, that if we ever work with an indefinite integral, we must get a constant of integration. Second, the definite integral. When we work with the definite integral, once again, we have to go through the whole techniques of integration, but this time, since we have a definite integral, we don't need the constant for that antiderivative that we find. So this is how we're going to work with these particular integrals when we're working with these vector-defined functions. So on this example, what we want to do is we want to calculate an integral. So I'm going to say evaluate the integral of r of t dt, where r of t is going to be t cubed negative 2t divided by t squared plus 1. And the third component is going to be cosine squared of 3t. There we are. So this is going to be what we're looking at when we're trying to evaluate this integral. So in order to do this, again, we're going to go with the integral. So here goes the integral. And again, this is going to be an indefinite integral. So the indefinite integral, because we have no bounds, is going to be the integral for the vector function of t cubed negative 2t divided by t squared plus 1, and the last component, which is cosine squared of 3t. And this is all going to be with respect to dt. Now again, the way we take these integrals is going to be component by component. So I'm going to integrate the first component, which will be t cubed dt. I'm going to integrate the second component, negative, I'm going to factor out that negative, so negative integral of 2t divided by t squared plus 1 with respect to dt. And the final integral will be the integral of cosine squared of 3t dt. So here are my three integral components. Okay, very nice. Now let's go through these integration properties. So the first component, let's see, if we add 1 to the exponent and then divide by that new exponent, we get 1/4 t to the 4th, and this is going to be in the first component. So there we are. Secondly, we're going to go with this integration, or with this integral. Now, this integral might not be too direct. However, we can make a u substitution. So what I'm going to do is, I'm just going to do the work on the left-hand side. Sorry, on the right-hand side. All right, so let's do the work on the right-hand side. I'm going to make a u substitution. I'm going to say that u is equal to t squared plus 1, and therefore du will be equal to 2t dt. Okay, perfect. So using this substitution here, I still have negative integral, and then that 2t dt, that becomes du, and that denominator just becomes u. So this is 1 over u du. And then finally we have cosine squared of 3t. Now, if you remember your power reductions, we have that a power reduction that we can have for cosine squared, and I'm going to put a little asterisk here, that cosine squared has a power reduction. If we use cosine squared of theta, then we naturally get 1/2 multiplied by 1 plus cosine of 2 theta. Now, using this sort of substitution, then we can go through and we can start extracting the values that we need. So let's start that extraction. For our problem, we don't have cosine of theta, cosine squared of theta. We have cosine squared of 3t. So making those appropriate substitutions here, I'm going to get 1 plus cosine of 2 times my angle measurement, but my angle measurement is 3t. So in this case, 2 times 3t should get me 6t. There we are. Looking pretty good so far. Now this is the integrand that I want to integrate. So I'm going to go here to my last line, and I'm going to insert what I just found. That is 1/2 multiplied by, and you know what, let's factor out that 1/2. 1/2 multiplied by 1 plus cosine of 6t, and this is all going to be dt for that particular substitution that we made. All right, now it's not really a substitution, it's more of a power reduction, which means it's an identity which uses the same variables. That's why I'm not really calling it a substitution, it's more of an identity replacement. All right, so we have again the first integral, or the first component done. So that first component was pretty straightforward, not too bad. However, the second component, this is where it starts getting a little choppy. Integral of 1 over u. Well, if you remember Calc 2, or maybe Calc 1, depending on where you took it, if you remember the integral of 1 over u, that is going to be the integral of the absolute value of u. Please don't forget the absolute value. All right, negative because that component was negative initially, and now I'm going to integrate my last component. So that's now going to be 1/2 multiplied by the integral of 1 with respect to t, that's going to just be t, plus the integral of cosine. Remember, its antiderivative is sine. So we're going to get sine of 6t, And remember, we have to use the chain rule, so when we integrate, we have to counteract that chain rule. So we get t plus 1 over 6 sine of 6t, and there's my integral. Now, we have to be very careful because we still have a constant of integration. And this constant of integration is a vector, so please make sure that we denote the constant of integration as a vector. Once we're able to do this, let's go ahead and clean all this up. Okay, so we're going to clean all this up. My first component is still 1/4 t to the 4th. My second component is now negative natural log of u, absolute value of u. So u is t squared plus 1. Notice t squared plus 1 is always going to be positive. So I don't need to write the absolute values. It would be a little bit redundant. I mean, if you want to write them, that's perfectly fine. And the last component that I have is going to be 1/2 multiplied by t plus 1/6 sine of 6t. And that's my initial vector, and then I still have plus c. Again, this is going to be my vector, my constant vector. So there you have it. That's how we work with these vectors, where we start applying these calculus techniques that we've learned so far. Now that we have a little bit better feeling for this, let's go ahead and let's start working on some more examples that will then start implementing all of these techniques. So let's work with this first example. This is going to be that we want to find a derivative of a function. So I'm going to have this as two different parts. The first part, part A, find the derivative of r of t, which is equal to 1 plus t cubed in the I component, plus t times e to the negative t in the j component, plus sine of 2t in the k component. All right, so this is the first integral that we want to find, or sorry, the first derivative that we want to find. So we're going to go through the whole process again. Taking the derivative with respect to t for r of t would imply that we need to take the derivative of each individual component. So we're going to take the derivative of each individual component. Oops, sorry, that's the I component, plus the j component, which is the derivative with respect to t of t times e to the negative t, plus the derivative with respect to t of the last component, which is sine of 2t. So that's j component and k component. There we are. So let's go through and let's run through that process. So we have on the left-hand side of this equation r prime of t. First component, that derivative is going to leave us with 3t squared, and that's in the I component, plus, now I'm going to need a product rule here. All right, so I'm just going to denote here we need a product rule. And using this product rule, we're going to take the derivative of the first, which is just going to be 1, so that's going to be 1 times e to the power of negative t, plus the first function, which is t, times the derivative of the second. So e to the power of negative t is a derivative of itself, and then you take the derivative of the exponent because it's negative t. That derivative will give us negative 1, so we multiply by negative 1. And all this is in the j component. All right, so again, we used the product rule here. Now for the third component, all we need is a chain rule. So we're going to apply that chain rule. The derivative of sine should get us cosine of 2t multiplied by the derivative of the inside, which is just 2. And that's in its k component. So all we have to do is just clean up this particular term, which is the j term. Let's clean that up and let's see what we get. So r prime of t, this is going to be equal to 3t squared in the I component, plus, I see an e to the power of negative t, and that's what I'm going to factor out. E to the power of negative t, let's factor that out, and we're left with 1 minus t. There we are. And this is all in the j component. And then the k component, as we said, was 2 cosine of 2t. And there we are. There's our derivative. Awesome. Now, let's go through and let's find something more unique. So what if we wanted to find the unit tangent vector of r of t at the point, or at the point where t is equal to 0. All right, so we have a little bit of work to do here. First of all, I want you to recall what is the unit tangent vector. Well, I did not mean to erase that. So here we go. I want you to recall what is a unit tangent vector. And again, that unit tangent vector, we introduced that around section 12.2, where we started introducing vectors. The unit tangent vector is taking the vector itself, or sorry, the derivative of the vector itself, and then dividing by its magnitude. Because if we're looking for the tangent vector, then that's going to be r prime. But if we're looking for a unit tangent vector, then that means we take the tangent vector and we divide by its magnitude. So once we're able to grab all this, we're going to go through and we're going to find this unit tangent vector. And what we're going to do is we're going to call this unit tangent vector capital T of t. This is going to be common notation moving forward, that if we have a unit tangent vector for a vector valued function, we typically want to denote it as capital T of t. And this will be a capital T in vector form. Okay, so here we go. I need to find r prime, but lucky for us, we already have r prime. So what we then need to do is we need to evaluate that unit tangent vector at t is equal to 0. So we need to take r prime at 0, evaluate that, and we need to take the magnitude of the derivative and evaluate it at 0. All right, well, let's go with the numerator. So the numerator, let's evaluate this. So 3 times 0 squared, and that's for the I component, plus e to the power of negative 0 multiplied by 1 minus 0. That's going to be in the j component. And then 2 times cosine of 2 times 0 is going to be in the k component. And to find this specific magnitude, what we're going to do is we're going to take each individual component and we're going to square it. We're going to add all those products, and then we're going to take the square root. So taking the first term, we're going to square it. So 3 times 0 squared, square that term. Add it to the next term, which will be e to the power of negative 0, 1 minus 0, square that term, plus 2 times cosine of 2 times 0, square that term, and then we'll take the square root of that denominator as such. So again, we got the vector in the numerator, and the denominator we have its magnitude, both evaluated at 0. So as we go through the whole process, you're going to see that the I component is no longer going to be there. The j component is going to be there, so we have 0i, and then we're going to have plus j, and then cosine at 0 should be 1, so that's going to be 1 times 2, so that's going to be plus 2 k hat. All divided by, well, let's see, The first component squared is going to be 0, so that's kind of nice. The second component squared is just going to be 1, so that's just 1 squared. And then 2 times cosine of 0, so that's going to be 2 times 1, which will be just 2. So 2 squared gets us 4. So 4 plus 1 should be 5, and we have the square root of 5. Now again, this notation looks kind of weird, and let me tell you, it is weird. So let's go ahead and let's clean it up, make this a nicer notation. This is 1 over the square root of 5. Oh, let's rewrite that. 1 over the square root of 5, and that's going to be in the j component, plus 2 over the square root of 5, and that's in its k component. And there it is. This is the unit tangent vector at the point where t is equal to 0. Awesome. Awesome, awesome. It's looking great so far. So let's keep working with this. All right, let's keep working with this greatness. So let's try a different problem now. In this example, I'll actually write this example right after. All right, so here we are. We're going to be looking at the curve r of t, which is equal to the square root of t in the I component, and then it's going to be 2 minus t in the j component, and we want to find the derivative of that vector curve and sketch the position vector r of 1 and r prime at 1. All right, so that's what we're working with. So let's go ahead and let's see if we can work through this. Now, what I'm going to want to do here again is I'm going to want to find its derivative. So again, let's go ahead and find that derivative, r prime of t. Take the first derivative, all right, the derivative of the first component. That derivative should get us 1 divided by 2 times the square root of t, and that's in the I component. The j component is then going to just be negative j. All right, or we could say negative 1 in the j component. So again, it's the instructions said that we needed to find r prime of t. Great, we found it. Now we need to sketch the position vector r of 1 and r prime at 1. So we need two different vectors here. The first vector that we're going to need is going to be r of 1. So again, r of 1, I am using the original position vector because that is my r of t. So I'm not using the derivative yet. I'm only using the first vector that was given to me. R of 1 should then get me, substituting square root of 1 is 1, so 1 in the I component, and then substituting in 1 for t in the j component, we get 2 minus 1, which is another 1. Perfect. Now I could write it as I plus j hat, or we can write it as vector components 1 comma 1. Now we need the derivative evaluated at t is equal to 1. So here goes, the derivative evaluated at t is equal to 1. Take the I component, or the x component for the derivative and substitute in the value of 1, and we should get 1/2 in the I component, and then still minus j. And again, vector component form, this is going to be 1/2 comma negative 1. There we are. So now we've actually extracted these two values, r prime, r of 1 and r prime of 1. So all we need to do now is we need to sketch those values. That's the last thing that we need to do. So let's go ahead and let's start on this sketch. I want to have a nice coordinate system here. So let's go here. There we are. So then this is going to be my y and my x. Now again, this is an x and y coordinate system because this is a two-component vector defined by I and j components. Therefore, only the x component and only the y component. So once we're looking at this, we can start identifying what it is that we want to sketch. The first one said sketch a position vector r of 1. So I'm going to grab that r of 1 and I'm going to sketch it. So r of 1, here it is. Let's do this in a different color, shall we? Let's do this in, I don't know what this color is. It looks like pink to me, so we'll go with pink. So 0, and I need a scale here. There we are. Okay, perfect. And then what we'll do is we'll go up 1 as well. All right, so there we are. All right, so there we are, 1 and 2. And this down here is going to be 1. Okay, and there we have 2. Okay, nice. Looking pretty good so far. Okay, so here goes my first component. Starting from the origin, we're going to go with 1, 1. So in the x component we go 1, and in the y component we also go 1. And so here is my position vector, 1, 1. And again, position vectors are measured from the origin. So this here is r of 1. Now the tangent vector. Remember, the tangent vector must be tangent to that given curve. So if it's tangent to that given curve, then I must have this vector r prime that is going to begin at the tip of r of 1. In other words, where r of 1 ends, that's where the tangent vector begins. So for the tangent vector, I'm going to do this in, let's say, orange here. And starting from where vector r of 1 ended, I'm going to go half in the x component. So from here we go to half in the x component, and then we go down by 1 value. There we are. So this vector now goes here. All right, here we go. All right. And here is r prime of 1. There we go. That's it. That's all there is to it. So now we've actually sketched all those position and derivative vectors that they were asking us to find. So we fully answered the question. Now let's see if we can unparameterize this curve to extract what is this given curve that we're looking at. All right, so let's see if we can go unparameterize all this. So we know that in the x component, we have the square root of t. And we know that in the y component, we have 2 minus t. Well, what if I square x is equal to square root of t? So in other words, square both sides of that equation. Then we wind up with t as being equal to x squared. And if we then substitute, so if we then make that substitution in to y, then we wind up with y is equal to 2 minus x squared. Check that out. That is a parabola opening downward, shifted up by 2. What does that mean? Well, parabola opening down, shifted down by 2. All right, there it is. And there's your parabola. This is y is equal to 2 minus x squared. Notice, did we find a position vector at t is equal to 1? We sure did. That t is equal to 1 finds that given vector. Is the orange vector here, r prime at 1, tangent to that given curve? Yes, it is. So on the exam, I could possibly give you a two-dimensional vector, or let's say a two-component vector, and ask you to generate all of this that we just generated. In other words, can you find the derivative in terms of t, which we did, that was the first task. Then, can you evaluate the position and the derivative at a given value? Once we did that task, then can you graph those? Can you graph them, and can you also outline the curve? That is going to be what I'm looking for. So keep that in mind when you're doing your homework. Make sure you pay attention to those types of problems. All right. This will give you deeper insight into what's happening when we work with R-Space 3. All right. So let's go on to the next example. And on this next example, we're going to be looking to find, let's say, symmetric equations find the symmetric equations for the tangent line to the helix with parametric equations x is equal to 2 cosine of t, y is equal to sine of t, and then z is equal to t, and we want this at the point 0, 1, and pi halves. All right, perfect. So there's a question that we have. And again, we want to find these symmetric equations. So these symmetric equations are going to be the equations of a line that we talked about back in chapter 12. And so again, we want to make sure that we are aware of all of that terminology that we were initially working with. So now that we have this, let's go through and let's start finding this. Okay, so what I'm going to do really quickly is I'm going to grab my vector r of t. My vector r of t is comprised of 2 cosine of t, sine of t, and t. Take the derivative because we want the equation for the tangent line. So taking the derivative here for this vector position function will now give us negative 2 sine of t, cosine of t, and 1. There we are. It's looking pretty good. Okay, now we want symmetric equations for the equation of a tangent line. Okay, so in order to find the equation of a line, we need two things. Number one, we need a point on the line. And number two, we're going to need a directional vector. Well, the nice part about this is that if we have a directional vector, or let's say in this case, if we have a vector position function, then taking its derivative will naturally give us that vector that we're looking for that will be tangent, and therefore it will give us the direction in which the tangent line will be headed in. So we need that piece first. So now that we have this, we just need some t value, because as it stands, we have the directional vector, but we don't have it at a specific point or at a specific t value. This is where the point that is given to us comes into play. Okay, so we need the point on the line. So what could naturally be the point on the line? Well, that's going to be the point given to us. 0, 1, pi halves. Okay, that's good. So that's done. Directional vector. Well, let's look at this point. Would you agree that given this point, we have some x, some y, and some z component. Well, look at your position vector. These position vectors give us the position for any point or for any vector shot from the origin or measured from the origin to the point in question. If this point 0, 1, and pi halves is the point that is on the helix and is also on the tangent curve, well, then that must mean that this position vector must reach that point, which means either 2 cosine of t is equal to 0, or sine of t is equal to 1, or t is equal to pi halves. Now, which of these equations will help us solve for t? That's a big question. Well, the answer is they should all help us solve for t. The very last one actually gives us the answer. They're saying, hey, you know what, there's no work needed to be done here. We'll give this to you for free. T is equal to pi halves. Okay. However, all of the other equations must also yield the exact same value. So let's see. Cosine of t equal to 0. Well, when does this happen? Well, it could happen at t is equal to pi halves plus pi k. All right, that's nice, but they give us a value here for t, which is just pi halves, so we don't need that pi k. And then we need sine of t is equal to 1. Well, t is equal to 1. Again, that's going to give us t is equal to pi halves plus, again, as we start moving through this, wait, did I say 0? Yes. Okay, perfect. So sine of 1, that should be, yeah, just pi halves. Wow, pi halves plus 2 pi k. And again, since they give us t is equal to pi halves, we don't need that 2 pi k. So all these answers lead to the exact same value. T must be pi halves. So if t is pi halves, let's get that directional vector going. R prime evaluated at pi halves. So here we go, R prime evaluated at pi halves. This is going to be negative 2 times sine at pi halves, cosine at pi halves, and 1. Let's see that directional vector. All right, sine at pi halves, we know that to be 1, so that's going to be negative 2. There we are. Cosine at pi halves is going to be 0, so there we are, and then we get 1. Do we have a directional vector? Yes, we do. Awesome. Okay, so now that we got that directional vector, what I'm going to do is I'm going to give the vector equation really quick. So the vector equation let's go vector equation of the line. I already have r of t, so we can choose a different value instead of r. So let's go with a. Vector a of t. Okay, so vector a of t, we're going to do this component by component. The x component is going to be the vector component of the point on the line, which is 0, plus t times the directional vector, so that's going to be minus 2t. Again, the y component for the vector position of the point on the line, plus t times, in this case, 0. Directional vector. Next one's going to be pi halves plus t. This will give me something real nice here. Negative 2t, 1, and then pi halves plus t. Looking pretty good. Okay, now if we want the symmetric equations, then we got to solve for t. So let's go ahead and let's answer this finally. So the symmetric equations. Solve the first one for t, so that's going to be x minus 0 divided by negative 2. So x minus 0 divided by negative 2, there we are, is equal to, solve for t here. Well, there is no t, t is 0, so we're going to leave that blank. For the next component, we're going to solve for t. So this is going to be z minus pi halves, all divided by 1 in this particular case. And we're also going to say that this particular piece, or in this particular case, that y is equal to 1. And again, y is equal to 1 because we don't have a t component. So these are the symmetric equations of the tangent line that is tangent to the helix, where the parametric equations are given by 2 cosine of t, sine of t, and t for the given point. There we are. It's looking real nice. Great, great, great. So let's work with one of the last problems that we have here. Or actually, we're not going to work with the problem. We're actually going to state a whole bunch of theorems. That way we can use these theorems at a later time. All right, so let's go ahead and what I'll do is some internet magic, and I will bring you back once I have this written down. All right, and here finally we have these rules for differentiation of these vector functions. And again, we are going to go through with these when we start looking, or how we actually start looking at these vector valued functions and when we take their derivatives. And some of the more important ones are going to be the ones where we have to use the product rule. More specifically, because numbers 5 and 6, we have two different types of product rules. One product involves the dot product, the other one involves the cross product. All right, so we have to make sure that we pay close attention to that, especially the cross product rule, because the cross product rule, as we saw, cross products are not commutative. Dot products are, which makes the dot product rule for number 5 quite straightforward, but number 6, cross products are not commutative, which means the function on the left needs to stay on the left, the function on the right needs to stay on the right when taking the cross product. After that, when we take the chain rule, then again, we always have to make sure we abide by that chain rule. So this is the final portion for this section. Now, if you stay tuned, next time we're going to be talking about these curves once again, but this time we're going to be talking about arc length. All right, so I hope you all enjoyed this lesson, and I will see you all for the next.